electron scattering part, people like Born, Oppenheimer, Bethe, Moore, Messe, all these people provided the foundation for the electron scattering theoretical works. So this is a little idea, just a little idea, but we should come to the present situation, who are the people working in various this kind of experimental experiments of electron scattering. Like there are many peoples all around the globe, but especially if I talk about India, like people like Professor R. Shankar and his co-workers in Banaras Hindu University. In TIFR, Professor Krishna Kumar, Professor Lokesh Trivedi, they do some kind of measurements of various cross-sections like elastic cross-section, ionization cross-section. Also for ionization cross-section, Professor Krishna Kumar, he does this kind of dissociative electron attachment studies experimentally. So now if you go to the theoretical works, like in India, I'll not talk about abroad, there are many people's working, you can see here, like there are different methods to calculate cross-sections. Like in the low energy, R matrix method is used, Swinger multi-channel, Cohen variational methods. At intermediate to high energies, spherical complex optical potential method, which is basically, which I worked out in my PhD with the group of Bobby Anthony at ISM, IIT Dhanbad for my PhD work. So there are many people working. In Gujarat also, people are doing this kind of study. And in Banaras also, Banaras Hindu University. So, so let's come to the introduction, why we are interested in this kind of study. Like, as you know this, like the electron is one of the most fundamental particles, which is found everywhere in the universe. So if you want to understand the interaction of electrons with atoms or molecules in various environments, you have to do this kind of collision studies. So this is one very nice paper in Science, which was published in 2000. And this was also kind of a motivation behind my PhD, where these people showed that the primary radiation, when it interacts with this DNA or biomolecules, they actually produce many secondary electrons. Like here you can see, they can produce many secondary electrons, and these secondary electrons are actually responsible for DNA damage break or strand breaks or single strand break, double strand breaks. So ever since this experiment, people have investigated electron scattering rigorously after this experiment. So the question which comes into mind is that what kind of collisional processes are happening? Like electron is there, atoms, molecule is there in various atmospheres, but what kind of collisional processes are happening? So if you want to look into that, broadly it can be classified into elastic and inelastic collisions. Elastic is where you don't have the change of internal energy of the scattering partners. These two have the same state as the initial state. And inelastic, broadly you can divide it into ionization and excitation. Ionization is basically where you have a target, you send some electron to the target, and if the electron energy is greater than the ionization potential of the target, it can ionize with the emission of 2 electrons. And excitation, you can excite it to some excited state, the target can be excited. But there are also various other examples of collisional processes like rotational excitation, electronic excitation, vibrational excitation, dissociation, dissociative electron attachment. So there are many processes. One just has to understand how to characterize them and what kind of collisional processes are happening in different atmosphere and study them. So, and all these collisional processes have one thing in common, like many things can be characterized by resonances. In electron scattering cross sections, one of the important features which comes into picture is the resonances. And resonances are some kind of a temporary compound state which forms when the electron interacts with the target, and there's a temporary anionic state which forms. And this resonances can be of two types, like shape resonances or co-excited resonances. I'm not going into the details, but this one picture you can see here, like why it is important is like you see here, like this is an ethanol molecule. This is the ethanol molecule, and you can see here, like if you want to break this ethanol molecule and get OH minus ion, you can send an electron of an energy 5 eV, and you can guarantee to get this particular OH minus negative ion. And if you want O minus, then you can get this, send this electron EV energy, and you can get O minus. So this is quite important, because if you want to selectively bond break the molecule, then you can you have to know at what particular energy resonances are happening. So all these collisional processes, all these collisional processes and resonances can be characterized in cross sections. So this is a very quantum mechanics textbook definition where you already have, once you read the quantum mechanics, you'll read this thing in the scattering theory. What is the cross section? Cross section is it's a probability, it's an area of finding that particular process. Like, what is the probability of elastic collision happening? So more the probability, more will be the cross section. So similarly, there are many processes, and those can be characterized by various cross sections. So it's, you can see here, this is the incident flux. B is the target. It's scattered into some solid angle. There's a detector, and you can divide the outgoing flux by the incident flux per unit area per unit time, and you can get the differential cross section. So once you integrate this differential cross section, you can also get total cross sections and other cross sections. So the applications are manifold. You can see there the applications are in various atmosphere. As I told you, to model various atmosphere, you need this kind of cross section. So atmospheric sciences, modeling plasmas in fusion devices, radiation physics, environmental studies, everywhere this is needed. From here, people calculate rate coefficients, and then they do plasma modeling and other kind of stuffs. So the methods which I have basically used in my studies are for low energies, I have used R matrix method. Intermediate to high energy calculations, I have used spherical complex optical potential method. And for ionization, we did develop this binary encounter method to calculate ionization cross sections. So I'm not going into details of the method, but I'll touch a little bit of spherical complex optical potential method, because this is you can understand how from the textbook these things are coming into research, and people are utilizing it to do some calculations. So the calculations are done for the gases, ground state atoms and molecules. So scope method is basically, as you know, like you have potential, you have a potential, you have in Schrodinger equation, you have that VR part. So basic idea is to construct the basic idea is to construct the optical potential. So the potential consists of real and imaginary part. Real can be static, exchange and polarization. Imaginary can be of absorption. So I'm not going to the details of the potentials, but this can be constructed from various model potentials. Once you have this potential, once you have this, sorry. Once you have this potential,
please go ahead, Dhananjay.
Okay, so once you have these potentials, you can put it into the Schrodinger equation and then solve it. So I'm not going to details of the potentials. This can be described. You can go into the definitions, but this is the things like static, exchange, polarization, absorption. These potentials are needed. So once you have the potential, you put it into the Schrodinger equation and solve it by the method of partial waves, and you get the phase shift. The phase shift is something which shows the signature of electron atom or electron molecule scattering or collision. So from phase shift, you can calculate this phase shift. Phase shift is coming from the potential. If you solve for free particles without potential, the phase shift will not be there. But with potential, if you solve it, then you will get the phase shift. And phase shift carries the signature of the electron atom or electron molecule collisions. So from phase shift, you can relate elastic as well as inelastic cross section here, and you can calculate this in this fashion, and then the total cross section is given by sum of these cross sections. So let's go to some sample results. I'm not going to details, but this is, as I told you, scope method is used for intermediate to high energies from ionization threshold to like around 2000 eV. So you can see here, this is calculated for chlorofluoromethanes, and you can see here the results for CCl4. The results, this is the experimental result, the symbol, and this is the theoretical method which we use, and you can see the agreement is quite good. And here we just plotted our data with the previous theoretical method of Jiang, and experimental data is this line, and you can clearly see the present method is a little better than the previous one. So this was quite good way to calculate cross sections. Then if I go to the low energies, like that was the intermediate to high energy. If I go to the low energies, you can see this was some of the works I did in South Korea. And you can see here the resonances which I talked about. This is the sharp feature in the cross section which is coming here. This is the result. This is called the shape resonances. And you can see the agreement is also a little bit, okay, it's better, or you can say reasonable. So this is the example of total cross section. Here we have plotted differential cross section. You can calculate differential cross section. The agreement is good. This is for C4F8 molecule. And also we did some kind of isomeric effect study, like the structure of the target can also have different cross sections. Like it depends on the structure of the target also. So for same C4F6 molecule, you can see the cross section is varying, and you can see all the targets have the shape resonances. And these targets were investigated for the first time because we could not find any data for. And this is the excitation cross section we could calculate from R matrix method. From like you can see, this is it's from 0 to 10 eV, and you can see also some kind of feature coming. This is basically core excited resonances. So and now if I go to the binary encounter Bethe method, I can see the results of total ionization cross section. As I told you, like every target, every atom has some ionization potential. Like you can see here, this is maybe the ionization potential of the target. And if you supply energy greater than that, then the target starts to get ionized, and the cross section slowly increases, reaches a peak, Gaussian peak, and it decreases sharply because the probability of interaction time becomes less and less as you go on high energy. So it slowly decays. So you have used, pardon? So we have used various methods to do the calculations, and you can see here the calculation for various C4FX molecules. And you can see as the target size is increasing, the cross section is also increasing. So the bigger the target, the bigger the cross section, because it gets bigger area for scattering. So here we have plotted the correlation plot of polarizability and maximum ionization cross section, because most of the targets were not investigated previously. So you can see the correlation plot is quite smooth and nice. So this gives us the reliability of the data, like it is consistent. So this is basically about cross section. So now I want to go to the work which I'm currently involved in, the Weizmann Institute of Science. And this is the picture. I just took it in the morning today, just to show you the experimental setup which I'm working. So this is a electrostatic ion beam trap. Now I'm trying to learn some experiments also and trying to do simulation. So it's a very wonderful experience because everything is new, and it just gives a lot of new things to understand. So you can see the instrument is this one, and this is the ion source. Like ion source, we have the optics here, and then we have a trap here behind the after the oscilloscope. I'll show the bigger version of this one. And here, this is the reason where the ions are trapped. So this is the mirror potential, where we apply potential in these two sides of the mirror. So it is called electrostatic ion beam trap because the ions are trapped due to electrostatic potential. The mirror, we have a mirror, this mirrors, and we apply potential to this. Like just to tell you, the ions comes from here. We lower this potential. Once it is lowered, the ions get inside. Once it is inside, we quickly switch on the potential and it gets trapped. Because this potential is always high, it goes inside, it oscillates back and forth. So once the ions are trapped inside, we can study various things like its dynamics, lifetime, many things. So just to show you the enlarged view here, this is where the trap is, and this is where the trap is, and this is the inside the trap, how the trap looks. You can see here, these are the mirror potentials. You see there are 8 electrodes, and here also there are 8 electrodes, and this is the field free region where the ions are trapped. So this is inside this one. I'll show you this. This is the trap, and inside this one you have this trap. So the ions are getting trapped here. So it's a very beautiful experiment and very new experience for me. And this trap has a lot of advantages. Like there are many traps like penning trap and some other traps, but this is quite easy to operate. No magnetic fields are there, a large field free region, simple to operate, and many more. So I'm involved in these things now, and the motivation behind this study is, like you see, once we apply the mirror potential here, we can change the potential. We can change the mirror potential here and here. Depending on the potentials, we can trap the ions in various modes. And these two modes, like dispersive and cell bunching mode, are already established experimentally. And just to tell you, like we send here we send the ions as a bunch, like we pulse it and we send as a bunch. So a few microsecond bunches of ions are going into the trap. Because this is important, because here you see this is the bunch width. The bunch is going in dispersive mode, it is going inside the trap, and with the time you can see the bunch width is getting dispersed, like there is nothing here now. The bunch width has dispersed, and this is plotted as a function of oscillation number. Like this bunch width, this is calculated and plotted, and you can see it is increases and disperses. And but opposite to this dispersive mode, in cell bunching mode, you can see here the bunch width, once you let inside this bunch in the cell bunching mode, the width is remaining constant. You see, like for 90 milliseconds have gone, but the bunch width is remaining constant. And this is because the EBIT is operating in different mode now, because we have changed the potential. So two types of potentials we are operating. So one is the dispersion, where the potential is steep, and here the bunches are getting dispersing very fast. This is due to the ion-ion interaction inside the trap. Just imagine in a room millions of people are trapped. What you can imagine? You can imagine that these people will have a lot of interactions, like they will be colliding here and there. Similar thing is happening here. Once inside the trap, the millions of ions are there and they are interacting now, and you have ion-ion interactions. So in one mode, the bunch width is getting dispersed very quickly, and in another mode, depending on the potential on the potential on the electrodes, the width is preserved. So
about
this
5
is
minutes more.
okay, ma'am. So this is very interesting, but you can see here in this cell bunching mode, the theoretical method is not in good agreement with the experiment. They could not explain it because they did not include ion-ion interaction inside in this model. So this was the motivation. So what we did was, like now I'm involved in this simulation also. Like we have created a simulation technique which can include the space charge interaction inside the trap. So this is based on the particle in a cell code, and here we solve the Poisson's equation inside, and you can say it is a mimic of the experimental situation. Like simulation is made in that way, and we can study the space charge interaction now. So I'm not going to the details, but I can show you some sample results. This is the current result. This is like just few months back I got after a lot of hard work. Some results you can see in the dispersive mode. This is the experimental data, and we are trapping now SF5 ions, and you can see the bunch width is increasing, and the theoretical model is also quite it's not good here at this part. We have an explanation for this, but it's generally good in this part. But the most beautiful part and satisfactory part was the self bunching mode. You can see the experimental data is the symbol which is constant. As I showed you, the bunch width is preserved. This is the bunch width is preserved in this mode, and the simulation is also giving us exactly the similar behavior. So this is a very encouraging results which we have. And then we can, again, now we have in the simulation, we can trap different number of ions, like 5,000 ions, 10,000, and we can see how when we increase the number of ions, this is without space charge, you can see it is very low. The bunch width is going very slowly, full width half maxima. And once we start increasing the ions, the dispersion is becoming very fast. And in the cell bunching mode without space charge, you see the bunch width is increasing like here, but once we put space charge and with number of ions, the bunch width is kind of a constant. So this is basically due to Coulomb repulsion. I have no time to explain you, but this is due to Coulomb repulsion. Like there are you can have a look at here, but this is due to Coulomb repulsion. Like the slower ions oscillate fast, and the faster ions oscillate slower. So this is a beautiful physics here. So there are a lot of things one can do with the ion traps. I have just shown you trapping dynamics. There are many things like cluster dynamics, other things you can study. And I just go through some like opportunities, like in ITER, just to touch this part, because I worked in some fusion related topics also. So in ITER, you can there are a lot of opportunities. It's a one-time project. It's a very big project where people are trying to create a virtual sun in the lab. So in France, this is going on, and there are a lot of opportunities here if one is interested in plasmas, in fusion technologies. So if it is successful, you can imagine a virtual sun in the lab, and it can get minimum input and produce maximum output. So this is a picture of a tokamak inside that heater, and people are trying to confine plasma in this tokamak, and this is a very challenging situation, because to confine it for longer times, if they can confine it for longer times, then most of the things will be eased out. So with this, I'd like to acknowledge all my colleagues from South Korea, all my colleagues from India, South Korea, Israel, Professor Odey Devar from Israel, Dr. Myung Song, South Korea, Professor Bobby Anthony, Professor R.K. Thapa, Professor V. Madhurima, Dr. Amitabh Bhattacharya, and many more, because these are the people who helped me shape my career in this way, because initial period we were in Mizoram together. So, and in St. Joseph College, I was there with Dr. Amitabh Bhattacharya, Dr. Pragati Pradhan, Dr. Divya Prakash Rai, and Madhav Prasad Bhimire. So all these people have helped me shape my career. So with that, I'd like to thank you. So
thank you very much, Dhanuj. That was, I think, a very comprehensive introduction to scattering, and you have given the audience an idea of where they can work and how they can work. So it was really nice. If there are any questions, we can quickly take a couple of them, a few questions.
Hello, ma'am. Namaste. Your student here.
Yes.
Yeah, so I have just one or two general questions to Dhanuj. And Dhanuj bhai, it's really a very nice presentation, and you did a very great job in completely different field of what we are doing. So that's really nice. Being from the same university, what we are doing, spreading in different areas. So thank you once again first. Okay, so I could not notice the slide number, but you have shown EIBT.
Yes, yes, sir.
So can you just show me the slide? This slide, please. Yes. So in this case, yeah, when I was looking this one, you also mentioned about this. Yeah, exactly. So dispersive mode. So I was imagining that if for the first column, what you mentioned was the ion accumulation, wherein there is some sort of curve, downward curve. So does that represent, my first question is, does that represent that all those ions are accumulated in such a way that they are in a very small area, and then you shot it out? What is the main physics there?
Which one?
Yes, the position where right now you have shown. Can you please go back again? Yeah, here, yeah, exactly that. The undercurve, which is
let's represent in each one of yourself.
This is just due to the polarity of the polarity of the trap. I can just show you. This is an old experiment. I can just show you another thing here. Like you can see here, the same peak are like upwards now. So this is the bunch we are putting inside the trap. Like we are sending the bunch. This is the bunch of ions we are sending inside the trap. Like we are pulsing it and we are sending it into the trap. So there is nothing to do with like something like physics here. Like it is just that we are sending the bunch of it to study how it is evolving with time. In one case, we are finding it dispersing quickly. In other case, it is getting preserved over a long period of time. Like in this case, you can see here, the bunch width is preserved.
And can you also count the number of ions that has been accumulated in that specific area? Is there some way, or you just have a general view?
In the experiment, we cannot now we cannot say exactly what number of ions, but we can apply the radio frequency RF to the trap, and then we can rebunch it. We can, like, once it is dispersed, we can rebunch these ions by applying external force like RF. We can rebunch it, and then we can see that RF amplitude, how much intensity it has. If the intensity it has high, then there are more number of ions. But we cannot say exactly what number of ions is there in the experiment. But in the
Okay.
simulation, we can do
I
the
see.
simulation with as many ions as possible. Like we can select the ions. Yeah.
Okay, so another question related with this one. So when you are accumulating the number of ions, so what it happens is that when they are colliding with each other, right? So the
Yes.
interaction between them will generate a very high Coulomb interaction, right?
Yes.
So because of that, the number of ion that is penetrating, so I believe that there will be significant reduction in that as well. So how do you deal with that? And I can see the curve, just if I look, you have shown one curve just next to this slide probably. Yes, here. So here at the beginning, for a very small time short, they are rising and then decreasing, and suddenly they are increasing, which I believe is due to Coulomb interaction.
We cannot say the Coulomb interaction is happening all over the place. Like it's not here only, but
of course, yeah.
it is
But
happening
when the area is small, I believe it will be higher, no?
Obviously, if the area if the distance is short, then it will be higher. But I believe this is basically because the initial distribution of ions, they have some initial velocity distribution, and also its position is little bit different. So there is some correlation between those two things. I don't know exactly how it is contributing to this one, but it is due to that velocity distribution of ions and its position distribution initial in the that.
May I suggest that you take this off
Yes, thank
privately?
you. Yeah, thank you. That's a good response. Thank you.
You can send me email.
Yeah.
Sir.
Any other questions? I would request you to please email Dr. Gupta, because let's keep to the schedule. It's late into the night. And thank you, Dr. Lalaj, for a wonderful presentation. It was really good. It's indeed my pleasure to be introducing the next speaker and the person who's going to give the keynote address for this entire international conference session, Professor Paulos of Department of Physics of IIT Guwahati. Professor Paulos has done his PhD from Physical Research Laboratory, Ahmedabad, and his research focuses on the very fundamental building blocks of the universe, the field of research known under the name of high energy physics, which is stylishly called HEP, which deals with the dynamics of elementary particles. He has numerous international and national publications, with the recent one being in Physical Review D, which was titled Relaxing LHC Constraints on WR Mass. Currently, he has 3 PhD scholars working with him, and 6 of them have been awarded PhD degrees, and he has mentored 2 postdoctoral fellows, and he's a fairly well-known person working in the field. It's our honor to be requesting Professor Paulos to deliver the keynote address. Please. Professor Paulos.
Yeah, thank you, Professor Madhurima. Can you hear me?
Yes, we can.
Okay, good. So I will try to share my screen and then start. Okay.
Yes.
Very good. So thank you for this initiative, Amit, Madhurima, and all other organizers of this meeting. And I'm really happy to be part of this and share some of the things that I have been actually thinking about in the past few years or a couple of decades in a way. So if we look around, we can see many different things, very complex things as well as simple things. But then what we have learned in the past something like 100 years or so is that underlying this complexity, there is some simple scheme, a simple structure that we can build, starting from the basic elementary building blocks. So we are familiar with this. All of us know that things are made of molecules, and then molecules are made of atoms. Atoms have nucleus, and nucleus is made of protons and neutrons. And what's not so familiar with in terms of common knowledge is that even protons and neutrons are made of substructures called quarks. So how this is the knowledge that we have kind of gained in the past century. Most of these things have been happening in the 20th century onwards. And how do we know these things? If we want to know what's there inside something, then one way to understand it is just break it, and then we will know what is there inside. So in some way, this is what has happened or what we do to understand the elementary particles or the subnuclear particles like proton, etc. Even the proton itself was kind of invented by these kind of experiments by Rutherford. So similar to the Rutherford's experiment where he established that the atom has a core called the nucleus, when we actually bombard these protons with even more high energy beams of electrons, and then that electron can actually go inside the proton, and that's what we have seen in experiments. And then it will probe inside, and then when we analyze the result of this, we can actually see that there are kind of granular structures there. It's not something like a cake piece of or a smooth disk, but rather it is it has granularities, or it has substructures there. And these substructures, when we study all other properties by, again, further experiments, etc., we see that they have, we can understand that other properties of this. And then what we know now is there are these quarks there. So, and coming to the forces or the dynamics there, we are familiar with electromagnetic force and the gravitational force, which is all around us in common day-to-day life. We can see that. But there are also other fundamental forces. For example, for the nuclear to be together, there has to be a strong nuclear force. And then for phenomena like beta decay, etc., we need what's called the weak nuclear force. So these things, these four forces, in fact, make are the only fundamental forces that we know about. This dictates the dynamics of everything that we see in our day-to-day life on Earth as well as in the vast universe. Now, we can make things from existing things. We can actually make physical changes as well as chemical changes. But in any of these, we don't lose anything. If you look at what is the number of atoms before and after, it remains the same. So then we have a question, we can ask a question like, where do they come from? Where are they made in the first place? And how does all these things happen? So to understand this, we have to understand the dynamics a little more, and then to the framework of the dynamics there at the atomic scales and below that, subatomic scales. And again, this is something which is quite familiar to all of us, that quantum mechanics explains the dynamics at the atomic scales. We can understand the atomic spectrum with the quantum mechanics, and all about chemical bonds to form molecules from atoms also can be understood from quantum mechanics. Then, and a variety of not just single atoms, but multiple or complex things like thin films or condensed matter systems, like thin films or extended metals, alloys, or ceramic materials, or anything that we consider. And in the recent times, even the nanostructures and the quantum dots, etc., all these things require quantum mechanics, or quantum mechanics allows or helps us understand the dynamics there, how things work at that level. And we have specialized techniques that we can develop. For example, the density functional theory that is employed to understand the electronic structure of many body systems. So some of these and many of these actually you will hear in this conference itself. Just now we heard talk on ion trapping and various aspects of this, understanding these things. All these require quantum mechanics. So we have fairly good understanding of things, how things work at the atomic level or slightly below that, subatomic levels, at the nuclear level. But again, it does not tell us anything about creating new particle or destroying or annihilating the existing particles. So we can only play with or rearrange things that is already there. And then in special theory of relativity, when we look at, basically we have a way of connecting this matter and energy. That's what Einstein told us. And quantum field theory, incorporating quantum mechanics and special theory of relativity, provides a framework to understand how all these things happen, how we can actually create particles where there was no particle, and how we can annihilate particle. For example, the beta decay. This is familiar to all of us. So if you look at the nuclear level of the beta decay, it's basically the neutron annihilating, getting annihilated, and creating a proton, an electron, and an antineutrino. We'll come to this antineutrino or antiparticles a little later, but just take it as an antineutrino, a particle. So this is something slightly different from the usual quantum mechanics, which in the sense that here we have a particle which is getting annihilated and we have new particles created. And quantum mechanics cannot explain this, but quantum field theory, yes, can do that. So that's what basically the framework or the basis with which we try to understand the entire particle dynamics. One way of looking at the or understanding this is, for example, the electron interaction, the usual Coulomb interaction. Let us consider the Coulomb interaction between two charged particles, say like electrons. So this, within the quantum field theory, we consider this, or we understand it as being happening with the exchange of the quantum of the electromagnetic field, which we call photon. And similarly, again, if you have a positron and an electron, positron is the antiparticle of electron, and they can get annihilated, meaning they can actually just vanish into some kind of form of energy, and this or electromagnetic field, and which is basically photons, collection of photons, and these photons can actually recreate other particles like muon and anti-muon, etc., or different quarks, etc. Okay, so quantum field theory has a well-established framework, mathematically, understood way of dealing with this, and it allows creation of particles and then annihilation of particles, etc. Okay, and the standard model of particle physics, we will not go into the details of that, but it actually incorporates all these things and then also tries to see what are the basic elementary particles that are required, and then we have a clear understanding of how things work at this level. Now, when we say that we have a clear understanding, it is not just theoretical understanding, it is also established facts by various different experiments. Just to give you give you an example, this recent discovery of the Higgs boson in 2012 actually happens when high energy proton beam collides with another high energy proton beam, and they get annihilated, two protons vanish, give a lot of energy, and Higgs bosons are produced from that and or generated there. And then these Higgs bosons further actually decays to say different things, 2 photons or 4 muons, things like that. And this we have actually experimentally seen at the Large Hadron Collider. We will not go into definitely the details of this, but I have kept some of this information here for students to see it later when Amit will perhaps share the slides. or you can also email me to understand more about it. So that actually kind of explains or gives us a fair understanding of how things work at this level. But usually when we look around, things does not happen just like that. Like things around us are quite stable. We are very stable. We don't really go into something else suddenly, although the quantum field theory allows all these things to happen. So when will it happen, or where is it happen? What are the conditions that you need to happen, this kind of thing? So we need special situations like what is there in the Large Hadron Collider. The environment has to be created there. Then we can ask the question, then where was this this kind of a condition in the beginning, or to start with, when all these things actually were made in the first place? So for that, we had to turn to the cosmology and the beginning of the universe. So cosmology is very fairly understood in the past 50 years or so. The development that we have in this field is tremendous. We have evolved the model, or the model of the universe, from kind of speculations to a precise theoretical framework, and which can be supported by various different experimental observational facts. So if you look at the evolution of the universe, then in the early stages of it, where the universe was in a kind of a very hot and dense, and high energy, very dense situation, where all these particles could be, elementary particles could actually be created. We don't still know how exactly these elementary particles were created, but we can actually start at the moment from where there was a kind of a hot, dense soup of elementary particles and a lot of energy. So from that time onwards, how the evolution, what is the evolution of the universe is very clearly, fairly understood, without too much of problems. But there are a few things which I will come to towards the end of this talk. Now, we know once in universe evolves and cools down, all these elementary particles can actually come down to form bound states, and then the bound state means the protons and neutrons, and then particles like units like that. And then further on, they capture the electrons as it cools further, and then becomes atoms, etc. And further higher, larger structures. And in this kind of way of forming the atoms, so we can actually make only the light elements like hydrogen, helium, and lithium, etc. And for heavier elements, we have to actually look at other places. We have now understood where it happens. It is the interstellar, not interstellar, interior of the stars. Like our sun, all stars generate this energy from nuclear fusion, which means that it combines different atoms or different nuclei. And in this way, we can actually form various heavy elements beyond helium, carbon, neon, and all other elements up to, say, ion. It is not possible usually to go beyond the ion, because ion, as you know, all of you must have gone through a nuclear physics course, and we know that ion nucleus is very stable. So going beyond ion it takes a lot of energy, and the energy that is available interior of the stars is not sufficient there. So where is this produced? Nature is fantastic. Actually, it has special situations and spectacular phenomena that we have now kind of somewhat clearly understood. This is when heavy stars, actually after kind of gravitational collapse to a certain extent and then accumulating or becoming quite energetic, explodes. This explosion of these heavy massive stars blows up all the elements not all the elements, I mean, some of the parts of these stars, the exterior layers of the stars. And not only that, it actually happens at high speeds. And there is a kind of, it sends the shock waves, and the shock waves have tremendous energy. And these kind of energetic situations is sufficient to actually produce even higher elements beyond iron. Like that is where all these heavier elements are made in the supernova explosions. So, and all of us, the solar system, all the planets and systems like that, other systems like that, everything is made usually from the remnants of the supernova explosions, and naturally all of this will contain the elements, including the heavy elements. So all these phenomena are quite clearly understood, but is everything understood? There are still missing links and things that we have not understood. So to talk about it, let us first talk about the antiparticle, although I mentioned the name. What is an antiparticle? Electron, we know very well, and it has charge in the units of the electron charge, -1, and mass, say 0.5 MeV in certain units. And there is another particle which has the same mass as that of electron, but opposite charge. So this is discovered experimentally. It is discovered in cosmic rays, and also it is discovered in laboratories now. In fact, we can actually make them, and we can also make other antiparticles in the laboratories. Similarly, for the quarks, there are anti-quarks. The charge, electric charge, is opposite to that of the particle, but the mass is the same as the particle itself. So for every particle that we have, there is an antiparticle. This, in fact, is required. It is a theoretical requirement. It is required for consistency. It is needed for the theoretical framework actually dictates that for every part electron, there is a positron, which should be there. And experimentally, we have now seen all of these antiparticles, which are predicted by the standard model of particle physics. So when particles are created, we can't create just electrons alone. One reason is that we will be actually creating charged particles, and then we cannot actually change the charge of the universe in that way, or we cannot. Charge is always conserved. That is one of the fundamental physical principles. And when we create particles and antiparticles, the charge is balanced, so as many other quantum charges or quantum numbers which are associated with these particles. So everything is okay in quantum field theory when we create a particle and an antiparticle together. So they are created like that. Not only that, they can also get annihilated, annihilate and then give energy. Now, this means that the universe, we had a lot of particles created and antiparticles created. They could also get annihilated, and then when they get annihilated, there won't be anything left how to make the nucleus, or the nucleosynthesis would not have happened. But we know quite a lot about the nucleosynthesis and how exactly this would have happened, and what are the numbers, how many of these things would have happened, or how many of these are kind of left behind in this and what's called the relic abundance of this now present in the universe. All these things are precisely measured now. And deuterium, for example, is one of the crucial things. As you can see the left side, the equations, the deuterium comes in many different, almost all these things, and it's crucial there. And the deuterium formation itself, it depends on the number of baryons, or the number of protons and the number of photons. So if there are a lot of photons, they will scatter, kick this barium, kick these protons around, and then will not allow it to form bound states or club together. So this is the problem. And then what is the number that is required is that for every photon, every proton, there will be something like 10 power 9 photons. So this is a small number, but there have to be there. So what would have happened, for example, is that there is a lot of matter and antiparticle which are antimatter which are created. They would annihilate but leave one particle per 10 power 9 or 1 billion photons. This is what is needed that we know from experiments, but we don't know how exactly this happens. So this is an open question still. What is the dynamics behind baryon asymmetry of the universe? Not only this nucleosynthesis, but there are other places, other evidence to where we have actually kind of clearly measured the baryon asymmetry, the baryon to photon ratio. So for example, if you look at the atomic formation, what happens at that where the universe cools down, all these electrons which are kind of highly energetic slows down, and then they can actually now be bound to the photons and other nuclei like nuclei, and that is the formation of the atoms. So these atoms are neutral, and the photons present there until then were interacting quite intensely with these charged particles, electrons and ions in this plasma. But once this plasma actually becomes a kind of neutral atoms, then the photons are kind of free, and this free electrons propagate just freely from then, and this we can see even now. So this is the famous cosmic microwave background, which was discovered in the 90s, and which was in fact one of the key evidence, experimental evidence, which actually established the Big Bang cosmology as the kind of a theoretical framework as accepted by most of the physicists now. And this is isotropic and homogeneous, but we have taken the photograph of this, photograph meaning the pictures of this, the data of this very precisely now, and we know that it is by and large homogeneous and isotropic, but there are small fluctuations. And then when we study these fluctuations carefully, analyzing it, and we see that we can learn a lot of things from this. We will not go into the details of how this thing is done, but I'll tell you what we know. We can actually, we know that the density, total density of the universe, energy density of the universe is close to what is required for a flat universe. Not only that, the visible matter that we know about, what is called the baryon content of the universe, is only 5% of the entire energy unit of the universe, and matter itself is only something like 32%. The rest of it is what's called the dark energy. We will not go into what it is, but coming to this matter, there is only 5% of this we know, we can observe. Rest of 27% of the energy density is what's called the dark matter. And we can also compute things from this. And for example, I mean, the baryon to photon number density, again, we can compute from this, which comes out to be again 10 power minus 9 as required in the case of Big Bang nucleosynthesis. This matching, this agreement itself is another evidence to actually, or another, yeah.
Less than 5 minutes?
Yeah, yeah, sure, okay. So then, so this baryon asymmetry is thus established, and we can actually understand, we have understood some of the properties of this. Again, let me not go into the details of this, but to just say that we have studied this and then we can understand it quite well, but we still don't know how exactly this can happen. In the standard model, we don't really have a way of doing it, but there are various theoretical studies that actually can explain some of, give some ways to address this problem. And but none of this is kind of established in terms of experimental evidence in that. Now, the other thing is this dark matter, which, as I said, 27% of the universe is dark matter, which we don't have any clue about what it is. Not only this CMB, but there are already other evidences like the rotational curve of the galaxies. Again, this slide is for you to look at later. But from this, again, we can see that the galaxies have or around the galaxies there are matter which we don't see otherwise. And there is also something called gravitational lensing. When we look at distant galaxies or objects from Earth, then we don't really see it as a point particle or point object, but we can see a kind of an annular ring or parts of this ring. This is called the gravitational lensing, which is possible if we assume that there is some kind of a localized matter which we don't see otherwise, but which exists on the way between these two, the galaxy and the Earth. And again, particle physics way of understanding it, we have been exploring various different things about it. There are specialized experiments to actually try to detect it. So far, we have not seen any of these. And there are various ways to accommodate this. They could be, we don't know anything about this so far experimentally, except that they are there. They could be spin zero particle scalars, or they could be fermions, they could be vector particles, there could be many different kind of these particles like these things. But we are kind of trying to understand all these things, and the explorations are on. Okay, so let me just kind of conclude this. So basically, in the past 100 and 150 years, we have really progressed quite we have our progress in this field of understanding what's around us and what is the universe is tremendous. And we have a kind of experimentally and theoretically explored and understood quite a lot of things. And we have fair understanding of how things work, how matter is made in the early universe, and how further structures are formed. But there are some of these very basic missing links, and we have to actually understand all those things to complete the jigsaw puzzle. And that's what we have been doing. And then all of you are also invited into this thing. And with that, I will end here, and thank you.
Thank you very much for a very, very nice introduction to simultaneously, I would say, to particle physics and astrophysics and quantum field theory all in one. I think we have time just for a few quick questions. There is one in the chat from Daslang Latmon who says, "Sir, can you explain the dark energy?" So would you like to take that?
Okay, so maybe that gives me dark energy. Dark energy, yes, I can only say one thing about the dark energy, that basically we don't know anything about it. Why is it called dark energy is because it is something which, see, usually the gravitational interactions pull the universe down, it attracts, and it actually brings it towards the center in a way. But energy, this dark energy is actually the one which is pushing the frontier further. So recently we have actually also seen that the universe is not only expanding, but it is expanding at an accelerated rate. Its speed of expansion is increasing. So which means that there has to be a lot of this dark energy there as well. So from the CMB experiment as well as from these recent experiments, we know that there is something which actually pushing the universe further and further, and then the universe is expanding further and further. But we don't know anything about this. It's if you know the Einstein's equation, there is something called the lambda that Einstein had used there, the cosmological constant which he had introduced. This could be that that actually does the job, but what is that we don't know. So all efforts are currently to understand what exactly is this thing.
There are plenty of questions coming in, and I don't think it's possible to take all of them because we are not over.
What you can do, you can actually share my email and then and the slides, and then they can contact me.
There are things about Higgs bosons and the anisotropy of CMBR and so on and so forth. I have a quick question before we close. The anions that was discovered a couple of days ago, would you like to make a comment?
I'm not sure about it. So basically the anions I know about it is that it's a spin, it could have any kind of spin, but
Okay.
this particular thing that you are talking about, I was not aware of. Which
I
is
think
this?
it was a news item a couple of days ago that they were discovered.
I see. So this I am not very sure about. But there is, okay. I mean, the only thing that I can tell you is in the fundamental elementary particle dynamics, there is no such possibility of any such ions. What's there? These anions usually come in the condensed matter systems where you can actually have these kind of systems that the particles that exist. But that's not really a fundamental particle in a way, but this discovery I have not really seen.
It was a brief news item, so maybe I'm not fully
maybe.
So,
okay. Just one question before you wrap up the session.
Yes.
Can I?
Quickly, because we are in shooting time.
Yeah, sure. So usually in cosmology, we assume that things are homogeneous and isotropic at the large length scale, right? But in short length scale, we know that things aren't that way.
Yes.
So I was wondering, like, do these short scale inhomogeneities and anisotropies manifest themselves in experiment in some way?
Yeah, that's what exactly I can. If the universe was completely isotropic and homogeneous, then none of the structures would have been there. Certainly, there was some small fluctuations, and these fluctuations are what we see in the CMB spectrum as well. And that's exactly what is the good news, that it was not completely homogeneous at small length scales, and then there are these small fluctuations. So if you look at the plot, I mean the figure that I showed you, and that fluctuation, these small fluctuations are sufficient to actually give all these different structures that we see now.
Thank you.
Right, thank you.
I think the rest of the questions you might address directly over email.
Yeah, sure.
Thank you for your excellent presentation. There are plenty of comments in the chat box, saying that it was an excellent presentation, which I think all of us would agree. Thank you again for presenting.
Thank you. Thank you, and all the best. Yeah.
Yeah. It's now time to move on to our third speaker, Dr. Arles Gil Rebaza from Institute de Física from Argentina, who will be speaking on density functional theory for study of materials. He has had his BSc in Physics and Mathematics from the National University of Trujillo, Peru, PhD in Physics, Institute of Physics, La Plata in Argentina. He has done his postdoc from the Institute of Physics, Sao Paulo in Brazil. He has been a guest researcher in the University of Pueblo in Mexico, Institute of Leibniz and Dresden at Germany. Currently, he is an associate researcher at Institute of Physics, La Plata in Argentina. He has over 30 publications in different international journals about material science, and he will be speaking on density functional theory and for the study of materials. The floor is yours, Dr. Rebaza.
Hello.
Yes.
Good evening for India. Here in Argentina is it's morning yet. So, can you hear me?
Yes, and we can see your presentation, so please go ahead.
Okay. Thank you to Dr. Amit for the invitation to participate in this first edition of the International Conference about the research advance in physics and material science. In this opportunity, I will talk about the density diffusion theory for the study of materials. Coulomb is Coulomb is more or less here in the globe. La Plata, Argentina is more or less in the another side of the globe, here in Argentina. There are 8 hours of difference. There are less here in Argentina. There is the Institute of Physics for La Plata. So, if we want to describe condensed matter like a molecular solid surface, a cluster, we need to describe different interaction about the electrons, nucleons, nucleus electrons, to describe different properties, physical or chemical properties of this system using quantum mechanics theory. So, to describe different contribution of the system, we need to add different components or different energy components to the Hamiltonian or the many-body Hamiltonians, like that kinetic energy of the nucleus, kinetic energy of the electrons, interaction nucleus electrons, interaction electrons, interaction nucleus. So we need to solve this Schrödinger-like equation where the wave function is complicated to describe because we need to describe the nucleus atomic position and the electron position to the whole system. So to solve this equation for a condensed system is so complicated because there are many variables to consider. There are analytical solutions only for many particles. So many particles, for example, hydrogen atoms and helium atoms, there are analytical solution for this equation. So we need to make some approximation to solve this equation. One of them is uncouple the electron part of the nucleus band or the wave function of the system. I need to discoupling or uncoupling the nuclear part from the electron part. Another approximation is a Born-Oppenheimer approximation. The idea is that nucleus is bigger and the electron is a lighter particle, and the nucleus I will consider fixed in my system, and the main contribution become from the electron part. So I reduce the the Hamiltonian to the kinetic energy of the electron, interaction electron-electron, and the interaction nucleon-electron. And now I need to solve only the electronic part. And another approximation is from the Hohenberg and Kohn theorem, where the wave function doesn't matter because the wave function of the system, there are no physical information. And we will consider the electronic density, electronic charge density of my system, that is this function. And this is the start point to describe the density function theory. Well, the Hohenberg and Kohn theorem, there are two theorems. I don't will talk about that, just to describe the main idea. The first theorem is about that if you have any observer, you can describe such a functional of the electronic density. All observer you must describe such a functional of the electronic density. And the second theorem is about if you can find electronic density to minimize the total energy, this energy belongs to the ground state of my system. So now I can express the Hamiltonian as a functional or a charge or electronic density, where the function of the kinetic part, the function of the electron-electron interaction, and the function of the external part. External part is the nucleus and electronic interaction. So there are some complicated mathematical expression to describe the kinetic functional part, and the electron-electron functional interaction. Nobody knows what is the expression to describe the electron-electron interaction. So we made another approximation where we will consider the kinetic functional of the homogeneous electron gas, and we will consider that the electron-electron interaction is described for a column interaction. So we add and rest this term, the column part and the homogeneous electron gas kinetic energy. And the difference of this functional of the kinetic part and the electron-electron interaction is called as the chain correlation functional. The chain correlation functional is the correlation of this hypothesis. The correlation, the difference in the true function of the electron-electron interaction minus the column functional is the chain part, and the correlation part is the difference between the true kinetic functional of my system minus the homogeneous electron gas considered. So we change the point of view or how to study my system. This is the many body description, the interaction between electrons and the nucleus or the core, the ions. And now we change to another description where I don't know where is the electrons. So just I know a cloud, something like a cloud, where there is the charge electron density, and I studied the interaction of this cloud with the ion nucleus. And another approximation is the constant theorem, where we change my initial system where the electron is interacting. There are a charge density corresponding to this system. So this system I will describe with an equivalent system, another system, equivalent system. Well, the number of particles is not equal. The number of particles is not equal, but the charge density is the same. In this analogous system, there are interaction of another particles called quasi-particle constant. There are no interaction between these particles, but the charge density is the same to the initial system. So this idea, we can reduce that. We can reduce this equation to equivalent equation, the one particle Schrödinger equation, but solving this self-consistent equation, we can obtain the wave function of the quasi-particle, and with this wave function or this quasi-particle system, we can get the charge density of this system, and this charge density is the same of the charge density of the original system. So to solve this constant equation, there are many approximations. There are two principal approximations to solve this equation: the linearized vector, for example, LMTO, linear muffin-T orbitals, full potential LAPW, B2K code, flare code, L code. And another very useful approximation is the self-potential plus plane wave method. For example, BASP code, quantum espresso code. And there are another approximation, but in some case the accuracy decrease. There are more faster, but the accuracy decrease, such FII-AIMS, Siesta, FPLO. So another is, what about the chain correlation part? The chain correlation part is the correction of the approximation that kinetic function that is described by the function of the kinetic cinetic term of the homogeneous electron gas. This is the chain correlation, and the difference between the true electron potential and minus the Coulomb functional considered. So the idea is to find this functional in order to decrease the difference between this approximation for the electronic interaction and this difference between the true cinetic contribution of my system. So there are many approximations to describe the chain correlation path. The field is the LDA. LDA is local density approximation. Well, the idea is that in some region the density is constant. This works for insulator and semiconducting system. But if you want to describe a metallic system or magnetic system, these files, we need to use another approximation. The GGA consider the gradient of the charge density. But if you upstairs this Jacob's ladder, you can describe better your system, but the accuracy increase. The accuracy to describe the system increase, but the computational demand also increase. So you need faster computers to use better chain correlation functional. And so there are a compromise between the accuracy and the computational demand. So in the next, I will show some example on how this approximation works and the capacity to describe some physical and chemical properties. In some case, theoretical results is corroborated by experimental one. There are some examples, and this is a magnetic alloys where our initial calculation describe the structural electronic and magnetic properties of this compound, and some years of the publication, people from India synthesize the compounds and can characterize the structure and the electronic part, and it match with our theoretical results. The same for this magnetic system. This was described using a linear calculation or field principal calculation. We determine the lattice parameter and the ground state the structural and magnetic ground state of this system, determine the lattice parameter and the total magnetic moment, and after that, experiment corroborate our theoretical results. This is a X-ray diffraction measuring, and this is a magnetization measuring. This is the case when theoretical result is confirmed by experimental one. This is the opposite when experimental studies are described by theoretical one, with this part of collaboration with experimental researchers. Well, they need to describe some experimental measures or some experimental results, but using ad initio calculation, we can describe this experimental results. This is the case, the case of this double perovskita. This is the case of the surface of this spinel system. And another case, or the last case is when the theory and experimental dance together, or sometimes also both. Well, theoretical research or ab initio calculation work together with experimental in order to describe some system, in this case, to describe the structural and magnetic properties of this spinel based on titanium, iron, and oxygen. We use in parallel ab initio calculation and experimental measurement, such as Sagnes and Mossbauer characterization. And this another example when the theory and experimental research work together. This to describe the covert absorption in this clay, monomerized. So this is all. This is my contribution to describe the main idea of how DFT works to describe physical and chemistry properties of different condensed systems. Thank you.
Thank you very much, Dr. Rabaza. That was a very brief and elegant introduction to the entire process of density functional theory and how it can be used for simulating various materials. And you did touch upon the various techniques that are available. Are there any questions for the speaker, please?
Hello.
Hello.
Hello. I want question, please, for Dr. Rabaza. Yes. Density functional theory work at 0 temperature Kelvin. What is the method that you use to make a calculation of phonons or Raman spectroscopy? What is the method used?
So, okay, this is a limitation of DFT approach, because DFT is, you can use DFT only to describe the ground state of the system, this implies that it's impossible to describe the dependence of the any observable function of the temperature. We don't describe this kind of properties. There are another
Sorry, somebody.
there are other approximations.
Yes, can you complete?
There are another approximations such a phonon to describe structural properties as function of the temperature. But
Okay, thank you.
Are there any more questions?
Hello, Dr. Moderiva, can you hear me?
Yes, I can.
Yeah, I just have one question.
Yes, Professor Thapa, please go ahead.
Yes, a very elegant and a simple method he has explained.
Right.
And he has a very nice publications and all in good journals. But he has not given any sort of a kind of a model. Like say, for example, in wine 2K, there is a FPLPW model is there. So I just want to understand what is the model that he has adopted or assumed in his DFT calculations.
Would you like to answer that, Dr. Abaza? What is the model that you have assumed?
no, I don't have idea about that.
All right. So maybe you can pose the question over email to the speaker.
Okay.
Hello, ma'am.
Thank you.
Thank you.
Hello, ma'am. Yeah. Can I just ask one more question?
Yes.
Yeah. Hello, Dr. Sir. I just have one basic question. You said that I saw in your slide that you are using a generalized RPA approximation. So I just want to. Hello, can you hear me?
Go ahead, we can hear you. You said that he uses generalized RDA model.
Yeah, RPA approximation. So I just want to ask you that how do you incorporate it in your calculation, like by using which type of computational codes?
So I can hear you.
Dr. Himanshu, would you like to take it over either the chat or on the email because he can't hear you?
Yeah, okay.
Okay.
Yeah, that might be better. We seem to have some audibility problems. So let us thank the speaker for giving us a very nice. Okay, there's one question that you'd like to take. How do you choose your stereo potential? Would you like to take that?
This a big question, big and hard question. So potential is something like a black box. Nobody know how it works. Just all people know that this works, but nobody know how it works. In some case, you need to test, perform many calculations of different systems, and test, and if this zero potential work for different tests or different systems, this is an option to choose this zero potential to use in another system or the internet system that you want to study.
Let's thank the speaker and thank you, Dr. Abaza, for a very interesting and brief introduction to the various methods of
Okay.
We come to the last presentation of the day by Dr. P. Pradhan, who's right now at the MIT Kavli Institute for Astrophysics and Space Research at the USA. He has his He's done his BSc from St. Joseph's College, Darjeeling, and MSc from University of North Bengal, and PhD from University of North Bengal and German Research Institute. He has done his postdoctoral fellowship from Penn State University, USA, and contributed to the building of software and algorithms for the next generation mission of he has worked very extensively in the area of data analysis from X-ray satellites like Suzaku, XMM, Chandra, New Star, Swift, and AstroSat. His research revolves mostly around timing and spectral analysis for neutron stars, both isolated and in binary systems, and their transient behaviors. And for his postdoctoral work right now, he is focusing on stellar wind diagnostics of OB stars and cool stars with the help of high resolution spectra from Chandra HEPG. He has a very interesting title which says Astrophysics, Neutron Stars and Animals. Wait, what? So we'd really like to know what. Dr. Pradhan.
Thank you, Madhura ma'am, for the generous introduction. I wanted to share a screen and okay, here it goes. So first of all, I'd like to thank the organizers of the conference, Dr. Amit Sankar, he's my junior. It's also great to see a lot of familiar faces, Dr. Samir Bal, Dr. Kultur, who was here earlier. I have had the good fortune to work with them for 7 years of college, and it brings back fond memories. I also see a lot of my former students, classmates, and some new faces. I recognize Dr. R.K. Thapa from Mizoram University, where I was there for a refresher course, and of course, many new faces. So it's great to be here. So the topic that I've chosen for today is deliberately a generic one. So I'm going to talk about astrophysics, animals, and pulsars. This topic was chosen taking into consideration the mixed audience that we have. So I wanted everyone to take away home some points from the talk that I'm going to present. Let me take you back to during the first days of astronomy, when astronomy was really used for navigation. So here in the picture, you see a human trying to find his way across the ocean, mostly because you don't have any landscapes in that case. So you would have to identify the direction, and one way to do that is there is always a star in the sky which is fixed. So with reference to a certain place, it is always at a fixed position, and that is how you identify the north. And any other direction will be like found based on this North Star. So what the human sailors used to do earlier was you would just point towards the North Star with something called a sextant here, and then you have a hanging cord that would indicate the direction in which the North Star is pointed, which would give you an angle with respect to the horizon. So once you know the angle, that is basically the latitude of that place. So you would know the direction, and you would know the place that you are. So this is how human sailors first use application in their everyday life. But the interesting thing to note here is that it is not always us humans who use astronomy. There are many other forms of animals, and that is exactly the topic of my talk today. Throughout the talk, I'm going to present you some animals which in some way or the other use astronomy or related science in their everyday life. The first one I'm going to talk about is birds. So we mostly know about navigation of birds. We know about it quite a lot now. So besides the fact that, let's say during short distances, what they do is they use the position of the sun. So you would know where exactly sun is during what time of the day. The sun is closer to the west during the evening, so you would know which is west, and that is how they would find out the direction during the day. And for short distances. But we know that migratory birds, they travel very long distances. So it's not really possible to keep track of where you're going. by only looking at the landforms. So this is an active field of research in which people are actually looking into what goes into the fact that these birds are able to navigate across continents and thousands of miles. And in some cases, they know exactly the error is so small that they exactly know where in which nest they are supposed to go. So the accuracy is great, and it cannot simply happen when you are only relying on the local land frames. So there are many competing theories. I present two of them here. The first one is there is a theory which states that possibly these birds have this iron oxide, the magnetite in their beaks, so that they are able to use the magnetic field of the earth to orient themselves. So once you know, if you are, let's say, going towards the south, so you would know in a way by your internal internally through the interaction of the magnetic field with the magnetite in your beak or in your head, wherever. So these compounds will actually allow you to orient yourself. So that is one competing theory. And another theory which has come up in recent years. So I was reading about it. This is about a protein called cryptochrome. So this cryptochrome are this protein in the eyes of this bird, which have a very interesting property. So basically what happens is, so when, let's say, photons strike these protein, it forms entangled particles. So you have two sets of, let's say, electrons with anti spins. So in that case, when these two entangled particles are formed, the only way for them to recombine is when you are oriented in a certain direction. Or in other words, you can think of this as the way so the bird will receive a stimulus in their brain when you are going in the right north-south direction, as opposed to, let's say, going in the east-west direction. And another video that I'm going to share, and hopefully it works. Okay, so this is when a photon hits, let's say, one of the atoms in the protein, and then it creates two entangled particles. And if you're going in the north-south direction, you will get a stimulus. The birds will get a stimulus in the brain that allows them to understand that, okay, this is the correct direction that I should be following. As opposed to, I'll show you another video here. So this is when you are going when the birds are going in the east-west direction. So the recombining the particles, the radical particles, the free radical particles don't really recombine with each other. So you receive a stimulus in the brain. So that's how this is a way in which birds possibly navigate through very long distances. And there are a couple of experiments that are being conducted. So the way to do this would be, you bring a bird inside a closed enclosure, and then you modulate the magnetic field of that lab, or a planetarium for that matter, and then you track, you possibly dye the feet of the bird, and then you just map its position across the space, in what direction it moves. So scientists are was working on this, and it is quite a promising theory, and it's actually cool. When I first read about it, I was like, okay, this seems to be like one of the many things how quantum physics comes, in our everyday life. So this is why I shared this with you. The another animal I'm going to talk about is, okay, so this is one of my favorite animals. These are dung beetles, and they are found in very hot places where very hot places like deserts, for instance. And these dung beetles have very simple life goals. So what they do is, they collect dung for dinner, which is basically what they consume, and then they roll them into balls. So once they roll them into balls, they take this this ball of dung to their house. And the way they do this is very interesting. So possibly because of the fact that their hind legs are very much developed, they literally climb on top of the dung, and then they have their hands on the ground, and then they push the dung, the ball of dung, in a straight line, but backwards with the hind legs. So it's very interesting to note how they actually find their way. And remember, because they are doing it in a backward direction, they prefer to travel in a straight line. Otherwise, you like, if you turn around, you may come back to the same place. So they would like prefer to travel in a straight direction, with their hind legs, like pushing their ball. I mean, that's their choice, sure. And the way they do this is they take a celestial snapshot of the band of sky across the sky. So, but one thing to note here is that these dung beetles, like humans, don't have we don't see a complete structure of anything. They have something called this compound eyes, in which they actually see different mosaics, and then they combine this together to form a complete image. Something like what you can see on the left-hand side here. This is for butterflies, also true for dung beetles and insects. So how do these animals actually, how do these dung beetles actually look up to the sky and find their way across is what, again, the scientists have been studying, and this is what they found. So this is a simulation of how the dung beetles would actually look when they look up in the sky. You can see a blue circle there. This is supposed to be a bright star there, which will be visible to us, but the dung beetles don't see it. So, once they roll on top of a dung, you would like the dung beetle will rotate around. So in that time, it's looking up to the sky, getting a feel for how the Milky Way looks that night, so that they can find their way back to their previous house. And for sure, we have to watch this dung dance. So it's getting on top of a dung. This is when it's probably taking the celestial snapshot, so that it knows its orientation with respect to the Milky Way and where it has to go. So this is a very interesting observation that has been carried on for dung beetles, and there are many other animals which do the same apart from dung beetles. For example, this is this is an experiment which was conducted in an enclosed planetarium. So you have two seals here, and these seals were made to identify the brightest star, which is Sirius. So they were rewarded when you would identify, when they would identify a certain bright star, because that's how powerful their eyes are. They are able to identify the bright stars. And then it was successfully proved that these seals are actually able to identify these bright stars when they're properly rewarded. So that there is your illustration of how useful rewards can be. The thing to note here is that these seals don't really migrate like birds long distances, but they definitely travel, like go for long walks, for instance. So it's useful to have them have their north known to them. Another one I'm going to talk about are the jumping spiders. Now, one thing to note about these jumping spiders are that they don't conventionally make a web like other spiders do. So the way they prey is by simply through their eyes. So you can see two pairs of eyes in the picture here. You have the secondary eyes. Now the secondary eyes are used to like really spot what is going around in the surroundings. And once you know there's something going on in this direction, so it will look in that direction, gauge what distance the prey is for, and then it jumps onto that prey. Now, one very cool thing about these kind of spider eyes are that they are similar to a Galilean telescope. So that means you have an eyepiece. You can focus all your light into a particular area in your eyes, which means that when these jumping spiders, like if they were to look up to the moon, this is how you would see. So to the left, this is what humans would appear, and to the right, if these jumping spiders would actually look up to the sky, they would see the moon in this distorted fashion. And also, another interesting thing to note is that given the spatial acuity, these jumping spiders are also able to see the nearest galaxy, which is the Andromeda. So that's just a cool fact out there, if only they decided to look up during the night. Now, I'd like to share this video here about how jumping spiders actually gauge their distances. Before I start this video, I'd just like to give you a brief introduction that these spiders actually have different photoreceptors in their brain, and these photoreceptors are sensitive only to one color, which is green. So they have very that's how they're adapted. They accurately gauge distances when it's the green color, but when you have like any other color, for example red, so they see red not as red like we do, but as a lesser form of green. So and again, due to the chromatic aberration in their brains, in their eyes, they just gauge the focus forms at a different distance than where the prey actually is. So therefore they miss the distance. So then this is an illustration. For example, this is for a spider, for a jumping spider under green light. So it catches its prey accurately. It knows where to look at. So it misses it. It's just a bad day. And the reason why this happened, as I briefly mentioned earlier, is because these photoreceptors are very sensitive to green light. And when green light is focused on them, they can really gauge the distance. But when they have a red light, the focus is at a difference from where it originally actually is. So it kind of gauges the distance in the wrong way. So that makes it like lose its dinner. So that was about spiders. The next animal I want to talk about are lobsters. Now, this is the best image of the lobster I would come up with when I looked in the internet. So these lobsters, something about these lobsters are, they are found on the base of the ocean, and they are pretty lazy creatures in the sense that they look around, they look for the prey, and then they take care of themselves by protecting themselves, but they do this without really moving their head. So what exactly makes these lobsters really like survive in the dark, deep waters without really moving around much is their eyes. So this is and you can use this you can like take an example of the lobster eyes and it has been used to really reconstruct X-ray telescopes, for example. So I should mention here that I'm actually an X-ray astronomer, which means that I look into these X-ray signals from space and then perform some science out of them. So the specialty of constructing X-ray telescopes are, to the left, you see an optical light. This is a normal mirror surface. If you have an optical light, it reflects. But you see, X-rays are very energetic particles, so they just pass right through. And the only way to reflect X-rays off the surface is to really incident them at a grazing surface, and that's how the X-rays are actually collected. In fact, you have dedicated telescopes inside many X-ray satellites that are used only for generating this grazing incidences of X-rays, because that's the only way you can capture X-rays. So the construction of X-rays are not X-ray telescopes are not really simplified as the optical telescopes are simplified in that sense. So this is how the lobster eyes come in. So look at the lobster eyes, they have a beautiful geometric construct. So the way this is obviously for optical light, because you can see it focusing even at other angles besides the grazing, the illustration here. So you can see that these eyes are actually made up of, imagine them as graph papers, as small square graph papers, but like all lined over your eyes. So the whole geometric construct is such that even when X-rays are coming from all directions at grazing incidences, you can actually focus them onto a common place from where we can get the image of the X-rays. So scientists are really using this to generate different kinds of telescopes. And one such illustration is, this is for an Einstein probe. It is being developed, and it's going to get launched possibly soon, in the future, in the near future. So you see the one in the lobster eye technology of actually creating different possibly CCDs in this case, are the one in green base zone there. That's actually like it replicates entirely the geometric construct of the lobster, such that you have, even if you have X-rays coming in from other directions, like if there's a transient that goes up in one portion of the sky, the X-ray telescope is actually able to capture it, because current X-ray telescopes are You have some all-sky monitors, but current day telescopes are like, they point in one direction, so they miss out what is happening on the other side of the sky. So it's really important to have the science returns of this kind of construction are very valuable, and all thanks to the geometric construct of lobster eyes that the scientists were actually able to copy this design. Okay, so the lessons that we've learned from these animal kingdoms are, you see the dung beetles, the way they process their eyes, they process their images in their brain, it's actually as small as a grain of rice. So these kind of like technologies are very important, especially in astronomy when you have to really deal with huge amount of image processing. We can learn about depth perception from spiders, maybe automate them for robotic vision. And lobster eyes is like geometric design of X-ray telescopes. These are some of the things that you can learn from animals. Now come back to humans. So how do we navigate? Right now it's pretty simple. You just have your cell phone, you have a GPS loaded there, and you know exactly where you should go. So I come to the second part of my talk where I talk about pulsars. Because clearly, if animals are navigating like the night sky through the Earth, we should do better, right? We as humans should do better. And one way to do that, of course, is pulsars. So this is what I have been extensively working on. I'll just give you a few second introduction of what pulsars are, for those who are not familiar with this term. So basically, these are so the way pulsars are formed are like when massive stars, they undergo supernova explosion, you have a remnant form in so you have a remnant, which are mostly made up of neutron stars. And mostly if their spin axis and their magnetic axis are not collide, magnetic axis are probably formed during the birth. So the spin axis, when they are not collide, every time the pulsar rotates, you would see a flashlight of signal from Earth. Something like this. Of course, you have to have a video here. So this is how pulsars look like, very close to each other. So those are magnetic field lines, those are beams of rays that you can see. And from Earth, this is how you would see it. From very far, you would see them as beeps of light, like a lighthouse. So these pulsars can be used for interplanetary spacecraft navigation. And what do I mean by that? What I mean by that is, think of this as GPS, but for space. So, for example, so right now, how interplanetary spacecrafts navigate is they always have to touch base with what is happening on the ground. So there are radio signal relays, and then the ground base on Earth knows what is happening with the satellite. Okay, maybe it has to maneuver to the left. Maybe there is a sun on its way, so it has to go in a different direction. Or maybe there are cases when the spacecraft just boom goes off. So these are different ways in which you have to know that by constant communication with the ground. But there is a way in which you can actually allow the spacecrafts to autonomously navigate through space only through the use of pulsars. Now, the principle is basically the same. What you do is you triangulate the position, just as we would do in a GPS. You would need 4 different receptors actually to locate your position on the Earth. So similarly, like if you have 3 pulsars that have like stable pulse profiles, that means they are like rotating at a constant frequency with a fixed period or near fixed period, you will get you will be able to locate exactly where in space you are. So the idea is to construct a pulse map, and then you allow your X-ray navigation, X-ray spacecrafts to just navigate by simply looking at the pulses that you obtain from 3 pulses. So you triangulate the position based on them. Now this is so in order to understand that, one thing we should know is you have to look at the pulse profile stability, which means, like, remember the earlier video that I showed you where you have different pulses of light. Now, when these pulses of light, so they come very fast, a millisecond kind of periodicity is what you have. So clearly you can't take care of every individual pulses, right? So what you do is pulses. So what you do is you combine these individual pulses Like you collect them together and then you fold them with the orbital, with the spin period of the pulsar. So in essence, this is the signal folded at the spin period, and this is what you get, what we call the pulse profiles. Now the pulse profiles are nothing but an integrated beaming pattern of extra pulses from the pulsar. And the good thing about this kind of pulse profiles are that they're very stable, and they're also very unique to each pulsar. So you'll be able to identify pulsars simply based on their pulse profiles. So this is one pulsar 1509-58. We took the pulse profile for many years. So we took it for like 15 years, and then we identified that how stable the pulse profile is. So the first thing to do clearly is to identify pulsars with stable periods. So you can now identify pulsars with stable period, and then you can like deconstruct them in order to generate their in order to look at their what do we call the composition, that is their the first harmonic, second harmonic, and so on, so that you can get a feel for the stability of these pulsars, like the way you deconstruct any signal for that matter. So this is what,
down to the last few minutes, please.
Sure. I'm just done. Thank you, ma'am. The way to do this would be, so we studied how stable the pulse profiles are, and then we performed some simulations based on what kind of spacecrafts are going to go up in space. You don't have to read through this. The takeaway point here is this: with this pulsar, you can achieve an accuracy of around 450 kilometers when you look at a pulsar for 15 minutes of observation. So the current field now is to really look into different pulse profiles and how stable they are, and which can be used really for spacecraft navigation and with what accuracy. And this technique has been known for a very long time. In fact, this is the map, this is the England record for what you placed in Voyager. For those of you who are not familiar, this is a spacecraft that was put ahead, I think, in the 70s, and they have like exact details. Let's say if an alien ever finds this in space, so they know exactly where to look at. So these are the pulsar maps here. So these are like an indication of like the 14 pulsars based on, and the lengths the lengths actually show what distance it is from the center of the galaxy, so that the aliens know how to find us if they want to. So this is idea has been there for some time, but it was only recently that the astronomers at NASA actually demonstrated this. So there is an instrument in the International Space Station called NICER, and this NICER conducted an experiment called Sextant to honor the previous previous sailors, human sailors. And what they did was they looked at different pulse profiles from different pulses, from 4 millisecond pulses, and they were actually able to find their actual position in space. So this has been a great like successful demonstration of what we can really do, and that is exactly where the future lies. So that is how I end my talk here, and I'll be happy to take questions. These are the references in case you're interested. And thank you.
Thank you very much for an absolutely fascinating talk, and you took me back to my childhood, where I remember watching these documentaries on dung beetles, and I didn't know about navigation using Milky Way, but yeah, the way they would carry the load, because their load-bearing capacity is much higher. This was a really fascinating talk, and do we have any questions for the speaker, please?
Yeah, am I audible?
Yes.
Yeah. Actually, what is quantum entangle and how it is related to your navigation of? You explained, but I couldn't find properly.
So the way I understand this is you can have so quantum entanglement actually refers to like, let's say you have two particles for that matter, and then they are entangled in such a way that they don't exactly have individual identities, but they are known only on the basis of how they interact with each other, in the sense that they exist together. So the way I have described it in my talk here is that when you have this photo sitting onto the cryptochromes for the birds, they actually form this kind of free radicals, and then they form two different, let's say, electrons with two different spins. And thank you. The only way that they can actually come together to form the original particle again is when the birds are moving in the north-south direction, and you have Zeeman effect based on the magnetic field of the Earth. So if you are moving in the north-south direction and you have antipolar electrons, you just combine together to give a stimulus to the brain, and that's how the birds know that they are going in the right direction. So that's how people have been studying.
Okay. Well, thank you, ma'am.
Are there any other questions?
May I ask a question?
Yes, please. This is Amitabha.
Yeah, I am Amitabh Bhattacharya from Sikkim University.
Please go ahead.
I have heard that desert ants also use the sun and the movement of the sun for navigating back to their holes after they have caught hold of food. How do they do it?
I see. That's first of all, I didn't know Dr. Amitabh sir. He's my mentor and my colleague. It's great to have you here, sir. I am not really sure. Like I haven't heard about desert ants, but if I have to take a guess, it could possibly be. So these different animals probably first of all look at the orientation of the sun with respect to the like what time of the day and where the sun is, so they can find out east and west. And some of these also have an ability to look at polarized light. So you know, the polarization varies with the different angle of the sun, so they can really find a way in which they can identify the direction based on polarization. So this is my random guess here. I don't know much about it, but possibly it's the sun and one of his ways. And all these things are really a combination of all these factors. So it could be landscape, it could be their olfactory sense, it could be the direction, it could be a lot of things. That's a great observation.
Thank you. Any other questions before we close?
Question. Hello.
Yes.
Hi, Pragati ma'am. This is Prashant. So, you I have a question. Like usually when we see the birds, they move in the flock.
Could you repeat your question? The question was not audible.
Am I audible now?
Yes, please go ahead.
So I think like usually when we see birds, they move in flock, or when we see the animals, they move in herds. So I was wondering, is there some kind of taxonomy into that?
The flocking and herding birds and animals.
I'm sorry.
Yeah, I mean, Prashant, your mic is not good. There is a lot of noise. But as I understand, he was asking if the flocking and herding, like the birds tend to flock together and animals tend to herd together. Please mute your mic. It's very noisy. Hosts, kindly please mute the mic. Dr. Pradhan, could you go? Okay, this another question which says you mentioned that the beetles easily identify bright stars when properly rewarded. What do you mean by properly rewarded?
Oh, that's an interesting question. That depends on what you want your reward to be. For example, for me, a reward would be a nice cup of tea. I don't know, for beetles, it could be food, for example, or proper I don't know, rest. So it could be anything that is appreciated by the one who's actually receiving it. So probably in case of serious, it was probably in case of the seals, it was food. That is what I would guess.
Okay, this question was with specific reference to the beetles. So yeah. All right.
Food.
Any other questions? If not, I would like to thank Dr. Pradhan for a very interesting talk. And the organizers for giving me this opportunity. And thank you very much. Back to you, Amit.
Hello.
Amit, go ahead. We can hear you. Please.
Okay, ma'am. Thank you very much, Professor V. Madhurima, for nicely conducting the session, coordinating the session. And in this session, we had 4 speakers, and altogether the session was very interactive. And I hope that participants are also enriched with the knowledge of the different fields, starting from the astrophysics to the DFT. So with this, I would like to thank our Professor B. Madhurima, and with this, I would like to conclude the session. And before that, I would like to request our principal, Dr. Samirbal, to say a few words about this session. Samir sir, please.
Hello.
Yes, sir, you are audible.
Yeah, sure. The session, we had 4 presentations, and they were beautifully done. Some of the presentations were for people like us who do not have a science background. I congratulate Dr. P. Pradhan, who was my colleague in my college when I was in the college. He's doing well. I thank Professor Polos for his keynote address, and I thank Professor V. Madhurima for chairing the session and conducting the technical session very beautifully. Thank you.
Thank you, sir, for concluding the session. So with this, we are concluding the day 1 session, this evening one, and we will meet tomorrow at 10 a.m. with a normal session for day 2. Thank you very much. Thank you, Principal, Coaching College, and our coordinator, the chairman of the session, V. Madhurima, and the speakers, Dr. Dhanuj Gupta, Professor P. Paulus, Dr. Arlis, and Dr. P. Pradhan Didi. Thank you very much. With this, we are ending the session. Thank you very much. Good night.